Consider again the equations of stellar structure. Taking the hydrostatic equilibrium equation, which is this one, let's make the crude approximation that the derivative of the pressure over radius is simply the pressure over the radius. That is, then we can write that pressure over radius is proportional to the mass over the radius square times the density. Then, if on top of that you assume that the density is constant, the density is the mass over the cube of the radius. Now, if you substitute this density into this equation for the pressure, then you have pressure over radius proportional to mass, radius squared times m over r cubed. So cut this with the square. We find that the pressure then must be proportional to the square of the mass and the fourth power of the radius. And you also know from the equation of state that the pressure is proportional to density times the temperature. Now, if again you substitute the density given by the constant density as a function of the mass and the radius, then you know that the pressure must be the thing proportional to the mass times the temperature over the cube of the radius. Now, to have both this expression and this expression hold, you must have then that m squared over r4, which is the right-hand side of this, must be proportional to the right-hand side of this, which is mass times temperature over r to the cube. Cut the masses and cut the radius and isolate the temperature. Then you find that the temperature must be proportional to the mass over the radius. Let's save this proportionalities that we found for the pressure and for the temperature. Okay, now let's play the same game with the temperature equation. Consider the equation for temperature under radiative equilibrium. And again, write that as just the temperature over the radius. And write the proportionalities. The proportionalities in this equation are that the temperature over radius is proportional to have a density here. So that's mass over cube of the radius. You have a temperature to the cube, have a luminosity, and you have a r squared. If you isolate the luminosity in here, you have that the luminosity is proportional to the temperature to the fourth power, radius to the fourth power over the mass. Now, if you substitute what you found for the temperature, then you find that the luminosity is proportional to the cube of the mass. Now, that is an interesting result, luminosity being proportional to the cube of the mass. Indeed, we know that more massive stars are more luminous than the sun. This is the actual mass-luminosity relationship for real stars. You see here, there is a clear correlation between the mass and the luminosity. For the mass of the sun, in here 1, you have a 1 solar luminosity. For 10 times the mass of the sun, you have about 10,000. So actually, the m to the cube is not that precise. In fact, the mass-luminosity relationship is closer to an exponent of 3.5. But that's an impressive agreement considering the crude approximations that we made. Now, from this equation for the luminosity, we can derive the lifetime of a star. If we assume that the lifetime is the energy over the luminosity, there is the amount of fuel divided by the rate that the fuel is being consumed. That is, you can derive a time scale given E over E dot, the energy over the rate that the energy is being liberated. The energy, you can say that is proportional to the mass of the star. And E dot is the luminosity. So as a crude approximation, this is the mass over the luminosity. Now, because the luminosity was proportional to the cube of the mass, then this is proportional to 1 over m squared. You find that the lifetime of a star is inversely proportional to the square of its mass. Now, this is a fantastic result, and even more remarkable considering the simple approximations that were done. The lifetime of a star decreases with the square of its mass. A more massive star has more fuel, but it burns it at a faster rate. This result is shown here. In the x-axis, you have the mass going from 0.1 to about 100 solar masses. That's more or less a range of the main sequence. And on the y-axis here, on the left-hand side, you have the stellar luminosity with the dashed curve So you can read here the luminosity given the mass in this dashed curve. It follows more or less the 3.5 scaling of the exponent of the luminosity of the mass. So 1 solar mass here, that's the luminosity of the sun, and 10 times the mass of the sun, you have it about here, 3.5. Now, on the y-axis on the right-hand side, it's the stellar lifetime, the solid curve. Now, this follows the m² curve. As you see, star of the mass of the sun has a lifetime of about 10 billion years, which is close to the age of the universe. A star that has a lifetime of 1 billion years is a star of about twice the mass of the sun. A star of lifetime 100 million years has a mass of about 5 times the mass of the sun. A star of lifetime 10 million years has a mass of about 20 times the mass of the sun.